Hi. So, my name is Alberto. Today we are going to talk about how we can teach computers to draw images and to generate very rich media representation, such as audio and video. And by the way, usually I do all my talks using a Dream Theater album, and incidentally, today is the 20th anniversary of this album, since from memory, was really pretty good. So, who we are, I work for a company which is named SourceSense, and we are a consulting company completely devoted to open source. We are in Milan, Rome, Cosenza, and London, and we deploy enterprise-level open source solution. We also are system integrators. Our expertise are in DevOps. We do Agile and also data science beyond Hadoop, and many more other things. And I want to thank them for having me here. This presentation, of course, is open source. You can download it, tweak it, copy it, rip it off, do whatever you want. So, our outline is really terse today. We will be talking mostly about unsupervised learning, exploring the three main models of generative AI, which are the fully visible belief networks, the variational autoencoders, and the generative adversarial networks. I know that most of you are here for that topic. And we'll explore some application of generative AI to image and audio. This talk is heavily inspired. I want to give my kudos to the Stanford CS321, which is the computer vision for deep learning by Stanford, and the Ian Goodfellow tutorial about the generative adversarial network, in case you're interested in the references. So we'll start talking about the supervised learning, which is the kind of task that we are already, everybody, all of us is accustomed to the idea that you have some data which is labeled, and you want to train your network to actually emit label on unseen data. And so this means that data is usually modeled by a tuple, and the goal is to learn a function to map from X, from your data, to a label. In this sense, I would like to recap once again what are the neural networks without all the brain stuff. In my opinion, comparing the neural networks to the brain hurts our understanding about how it works and just makes it more magical. So, once again, I would like to say a neural network is a class of mathematical functions which hierarchically stacks a series of linear functions, sandwiching these functions with non-linearities. And that's why it makes so effective, because these linear functions are kept separate, they don't collapse onto themselves, and they can learn non-linear, to classify things by non-linear hyperplanes. So when we talk that the goal is learning a function, we want to learn the coefficients of these mathematical functions, the parameters. And the supervised learning is practically everywhere. So we have it in classification, regression, almost all computer vision, basically, in which we want to recognize stuff, and almost all natural language processing. But in unsupervised learning, we only have unlabeled data. So this means that we don't have an idea what we want the network to predict. And the goal is actually to learn some hidden structure, some latent structure of my input data. And in my opinion, this is a lot sexier than supervised learning, because the unsupervised data is cheap. It's very difficult to build a training set with labeled data. Think about the segmentation stuff. It would be super expensive. You have to take images, manually segment it, and then that's one training sample. Or about the parallel corpora to generate languages. The ImageNet data set, it took a lot of time to crowd it all together. Instead, when you have unlabeled data, any data is fair. So you can train much bigger networks on bigger data sets, because you have a lot of it. And the practical applications are clustering, dimensionality reductions, in which we have very feature-rich stuff. We want to lower it on simpler realms, simple domains, in which we can more easily analyze this data. And we can do also feature learning. We have a lot of unstructured data. We want to extrapolate what are the features that we want to use to train a classifier onto itself. And of course, rich content generation. So deep generative models actually, given a training data, generate new samples from a probability distribution. In this case, we want to think that there is a distribution underlying which generates all our samples. This is the frequentist approach. And we want to train by maximum likelihood over the parameters to define the distribution. So we have a training data, and we try to get parameters to form a probability distribution that has generated the data which is part of the training set. And then we want to generate new data that may belong to a training set for the likelihood. So the goal is to learn a function, P model, as similar as possible to P data. So given the fact that data is originated by a probability distribution, which is hidden, we want to approximate as much as possible a model that mimics the real distribution. And then we want to generate new samples from the probability distribution model that we just created. So the generation starts as a density, probability density estimation problem in this case. Hope that most of you are at least a little bit comfortable with the probability theory in this case. Okay. So the idea is that we have a model and we can sample from this model. So get points that are actually originated by this distribution, that given how this distribution is modeled, we may have different samples. In this case, we usually use Gaussian distributions because it makes sense for how we want to model the problem. So all our models are actually divided in this taxonomy. The first category split is explicit density estimation versus implicit density estimation. So these are the models. Do we have a pointer here? Okay. These are the models actually which give us an explicit probability function that we may use to model and to interpret our data. Some of these density are mathematically tractable, and this is the category that fully visible belief networks belong to. In this case, the pixel RNN, CNN, we will see in a moment. Then we have problems which are mathematically intractable, and here belong the realm of variational autoencoders. And then we have other stuff which don't model explicitly the probability distribution, but they just work by direct sampling random images, and you cannot actually see what is the corresponding number below the hood. And this is the realm that the generative adversarial network actually belong to. So starting with a fully visible belief network, model use the chain rule probability to decompose a very complicated probability distribution that we are trying to learn over a vector of some dimensions into a product of one-dimensional probability. So we just say, okay, this phenomenon is actually generated by a very complex model, but if we factor this model over simpler components, we can actually approximate a model in which the last parameter you're trying to generate is actually conditioned over everything that you've seen before. So this is an autoregressive model, actually, something which is depending on the previous states and to a level of stochasticity, so a randomness on the current state. So in this case, if we want to estimate a pixel in an image, in an image self-contained, we know that the product of the single pixel conditioned of the values of the previous pixel we've seen is a good way to actually model this. And to learn this very complex probability distribution, we just use a neural network to express this distribution function as an approximator. That's why I want to stress it out that neural networks are mathematical functions, actually. The main drawback of fully visible belief networks is that samples must be generated one entry at a time, so one pixel at a time in this case, and it cannot be parallelized. because you're always dependent on the previous context that you have elaborated. Okay? So in this case, when we want to generate images, if we use pixel RNN, is a model that uses a recurrent neural network with an LSTM cell to keep the context, to generate pixels starting from the corner, and then in the second step we generate nearby pixels, and the subsequent steps we generate the nearby pixels based on the previous state. And in this case you can just generate an image conditioning on the first pixel of it, and you generate a picture of basically everything. Works well, but it is very slow, and another way to just avoid conditioning of just nearby too few data is using a CNN, which is another way to generate pixels, using as context a whole region that surrounds you by masking, of course, the state that you haven't seen still. So you just go in this way, like a linear raster, starting from this one and going in rows, and you just take the context surrounding pixel. Since this is a causal convolution, sorry, so that you just convolve with everything before you, but not everything after you, it forbids parallelization. But this turns out to be a lot faster of RNN anyway, because we are able, since this problem has an optimal substructure, it's a dynamic programming problem, and we can memoize. So we can actually keep track of the previous states and avoid computing everything for each step, but we just can cache the previous pixels. And this is the case that WaveNet uses actually. So WaveNet is a recurrent neural network, is a causal convolution neural network, used in a recurrent fashion, it's not recurrent actually, that generates audio one sample at a time through this dilated causal convolution. What it means that you just convolve these two pixels, and then you convolve one step back in time, and then 2 steps back in time, then 4 steps back in time. This is a trick to actually expand your receptive field, what you're actually seeing, how much in the past you're looking, by keeping the number of operations constant. And since this generates one sample for each forward pass, by generating 44,000 samples per second of audio, you're able to generate samples which are not distinguishable from reality. And I have a demo about that. So this is taken from the website of DeepMind, and this is a piano generated by WaveNet, and this is not an actual real piano. It's not a robot typing. It's actually audio generated completely from the computer. Get back. Were you able actually to tell the difference between this and a real piano? So this is the most realistic audio that you can get. The drawback is that it's really super slow, because it needs 2 minutes of computation to generate 1 second of audio, so it cannot be employed in real-time conversation. But actually, this is scaringly realistic, and you can really generate also voices, of course. And we have this one.
Sådan. Ved du, hvad jeg siger, jeg står til mig, og den er godt til noget. Så tager det til, jeg den forfatning, der godt kan det give så.
So all this blubbering actually is the neural network that doesn't know what to say, but it's emitting a very realistic waveform. So it really looks like a real person. The next kind of model I want to introduce you is the autoencoders. So the autoencoders work in a very different way. And these are kind of networks with that work by not modeling explicitly the probability, but modeling a mathematically intractable problem. And just forgetting the real nitty-gritty mathematical details, they work on estimating a lower bound, but not a real number between the probability. But turns out that that is enough to actually get out a real solution to the problem. So the autoencoders are a kind of neural network that project higher dimensional samples in a low compressed representation and then reconstruct the output. So in this case, we have this input, which is a matrix of pixels. You send it through an encoder, and the encoder gives you a vector of real numbers, so float numbers, basically. And this vector is a fixed representation, which is a dimensionality which is lower than the original one. Why? Because it prevents it to learn to output the very same, the identity function. And then feeds this vector, which is called the latent representation, to a decoder, and the decoder tries to reconstruct the input in this case. So you get a reconstructor which is as close as possible to what you had here. How do we do this? So we take an input, and we pass through a 4 layers convolutional neural network, and we end up with an array of features, of float numbers. This is my internal model, the internal representation of my input. Then we actually feed to a decoder, which is an up convolution. Don't say deconvolution. Each time I see somebody says deconvolution, my heart really cringes, because deconvolution is not the opposite of convolution. It means subtracting a signal from a convolved one. In this case, instead, we are trying to reverse the effect of the convolution, which is the downsampling. So it's up convolution, or transpose convolution, or fractionally strided convolution, because you use a stride, so a step, which is the inverse of the one. So since the stride is a positive number, the inverse is a fraction. And what we get here is that we have the encoder, which is a network that gives birth to these latent factors. And then we have these layers which reconstruct another image. And then you compare the input to the reconstructed output. And you compare pixel-wise the difference between the output, the input, and the output. And that gives you the distance that is able to use as a breadth propagation into your network. This is like our label data, but it's actually our input. So that's why it's unsupervised. You actually don't need a label. The label is the input itself. In case you're still not sure about how these features are, I would like to do a 10 seconds experiment. Close your eyes, please. Close your eyes. Imagine a forest, okay? You're in a forest. There are all the trunks, the branches that cover the cloud. Okay, now open your eyes. You imagine a forest, but if you were to draw it, it will be a little different. Or if you try to draw it again, it will be different from the previous. What you imagine are your latent factors. Are actually what the idea, the Platonic idea that you have in your mind about how the archetype of a tree, the archetype of a forest, how it should be. The network does exactly the same thing. So it has an internal representation of how things should be. And then when you actually want to, okay, draw me a forest, please, it samples from this very blurry distribution and gives birth to a real output. What are autoencoders good for? You're just able to generate what you input in. Well, this turns out to be very useful for denoising an image. In case you have a very distorted image by noise, you feed it into an autoencoder, and you reconstruct the image as it should be. If you have a picture with an inclusion, for example, you take a picture with your camera, but you have a finger over your lens, so there's a big finger inside the image, you feed it into an autoencoder, and it will just redraw the image as it should be if that finger was not there. So it's able to make up for occlusions, for example, for noises. Autoencoders also are very useful for semi-supervised learning. So we want to build a model. We have very few data. So what we do, we just initialize the learner by training an autoencoder first. So we learn the features of our data. And then once we have these autoencoders bootstrapped with ImageNet, for example, with celebrity dataset, for example, which is a lot of images, then we throw away the decoder, and then we impose a classifier. And now I use my very small data set, for example, the faces of my classroom mates at the high school. And I'm able to classify my schoolmates over samples of a data set of 100 images, which is really very small. But I was able to bootstrap, actually, the features that faces should have, actually. And then I'm able to compare my output of my classifier trained or my very small data set to the thing that I'm actually expecting, and then fine-tuning. This is a way to actually do a transfer learning using autoencoders when you don't have any labels or that. So what is the problem of autoencoders when generating stuff? Well, the problem is that for generation, the latent space may not be continuous at all. So in this case, I wanted to plot the MNIST. The MNIST is the handwritten digit data set. And each one of these colors are actual numbers. So this is the 0, this is the 1, the 2, the 3, to the yellow, which should be the 9. And I plotted the latent representation in a lower dimension by T as ni plotting. And you can see this is the space of 1, and this is the space of 7. But if I want to sample something, that belongs to 7 and 1, my autoencoder is perfectly able to do that because it has sufficient populated space. But if I want to sample something which is in between, I'm not able to, because my cluster was not, my classifier was not trained to actually recognize something which is at the intersection of two spaces. So if I wanted to, if I tried, it will produce garbage. Figures that make no sense. It's not recognizable as numbers, as faces, and as anything. So how do I do? Well, here jump in the variational autoencoders. The variational autoencoders learn actually a probabilistic distribution, which is Gaussian in this case, that we use to generate a sample that then we use to decode over the output. So instead of actually learning the features here, what I learn is to create the mean and the variance of my Gaussian distribution. Then I sample from my probability distribution. And the sample is actually my latent vector that I feed to the upper layers to up convolution. And I have an output, which is a new output. It's an interpolation, actually, of what I had. So this is a way to actually generate new stuff. At inference time, we use the decoder only. We start with Z of our choice. So we have, this is the training, actually. Okay? And then we have trained the layer to output an image given a Z, which is different each time. So if I just define a Z with a normal distribution, zero-centered with one variance, I'm able to sample new images. And hello? OK. This is an example. So just let's just suppose that I have two, my Z vector is actually two variables, Z1, Z2. If I turn the knobs over these vectors, I'm able to variate how the numbers are generated by turning the Z1, Z2, which are real value, float numbers. So changing the float numbers, my output changes radically. Here's a magic output of an MNIST trainer model. Note that since we are using a L2 loss, so it's the squared root error that punishes big mistakes and is very, very permissive with small mistakes because it's squared. So 2 becomes 4, and 0, 1 is 0, 0, 1. So the mistakes below 0 are actually very well tolerated. You have blurry contours. So the image is not sharp, precisely because our loss function is permissive of small errors, because the L2 function is permissive. Or small errors and just punishes big errors. And now that we know how variational autoencoders work, actually, we know how to do deepfakes. So deepfakes, technically, is a pair of autoencoders with one shared encoder and two distinct decoders, T and B, T for Trump and B for Baldwin. I chose Alec Baldwin because he makes brilliant imitations of Trump on Saturday Night Live. So the idea is that we train the encoder, shared encoder, with the decoder T on pictures of Trump, and the encoder, decoder Baldwin, on pictures on Baldwin. Okay? This is really a no-brainer, actually. We just learned to reconstruct the image of Trump and Baldwin. Then what we do is that at inference time, we feed the picture, of Baldwin to the encoder, and we decode with the Trump decoder. And what we get is that if I put inside a smiling Baldwin, I will get a smiling Trump, actually, because the shared encoder is able to capture the latent factors of the face, but the decoder is the one that actually generates the end image. So if you want to do a deepfake video, what you have to do is that you take a video, you just segment it frame by frame. Each frame is sent into this neural network, which outputs new frame. You recombine together. The audio, of course, is not changed. And you get some dancing person of your colleague over Michael Jackson, for example. And we train how? We take a lot of videos of Michael Jackson, a lot of videos of your colleague, and you end up with some decoders and encoders that are able to actually cope with the input data. So passing to the third model that we have today, we have the generative adversarial networks at last. GANs are based on a game theory approach, so two agents playing one against each other with a non-zero-sum objective. So the objective is not to have I win, you lose, or you lose, I win. And I was actually the same. But the idea is that I have to maximize, one has to maximize its own performance, and I have to maximize your debacle, actually. So it's not really a minimax game, it's not a zero-sum game. And the objective actually is not to win, but to find the Nash equilibrium. And the Nash equilibrium, if you have seen A Beautiful Mind movie, is a condition in which none of the two can win over another. So by sticking to my policy, and if you don't change yours, I cannot go beyond a certain level, and you too. So we are in a perfect equilibrium. So discriminator must we have a joint function that we try to optimize, which is a shared, shared parameters between the discriminator and the generator. And the discriminator can only control the parameters of itself, cannot control others one parameters. And the same goes for the generator. Generator has the same objective function, but can only control its own part. So I'm dependent on the moves of my adversary. And the architecture is really, everybody I think knows it. We have white noise feed into a network that generates an image. And discriminator must not be fooled by the generated image or the trained set image with a real, and must output a feedback whether it's real or fake. So discriminator must be able to catch the generator network and able to discern trained set images. And the generator must fool the discriminator network, of course. So the generator is just an upsampling network with transpose convolution. So we start from a small image with noise, and we generate a full high-resolution, super nice image. And the discriminator is just a normal convnet. This, from Radford et al. In 2016, laid down the basis how we should actually design the architecture. So we should not use the pooling layers in the convnets, but we should rather use the Strider convolution. And that makes a lot of sense, because when you have a convolution layer and then a max pooling in which you cut out, you crop a lot of the details, you're actually learning something, and then you're crippling the output of your network because you want to get a lower dimensional representation. Instead, it will make much more sense if we just learn to output directly the lower dimensional representation. Use batch normalization in both networks. Do not use fully connected layers, but that is actually was well accepted that we must use a convolutional layers, not fully connected. The generator uses ReLU everywhere, but in the last layer, which used 10H to actually output a number between 0 and 1. And discriminator uses leaky ReLU everywhere, so you don't have gradient clipping. We know that GANs are able to produce really high quality images, but the nice thing is that these images are actually generated each one by a different latent space vector, and this latent space vector admit the arithmetic manipulation. So if these are images generated by the network, smiling images, if we average the vectors that generated this one, we get this another image, which you can see is just a sum of this one. And if we do the same for all these images of neutral women, which is not smiling, we take the vector that generated the smiling women, and we subtract the vector that was used to generate the neutral women, and then we add the vector z that we used to generate the neutral men, what you obtain is smiling men. So we're able to translate, because the latent factors that are responsible to generate the smile survived in the arithmetic operation, while all the others actually died, went to 0. And this gives a lot of interpretability about how these neural networks work. So here I have my nice demo, in which this actually, the GAN paint is a byproduct of a paper which is called GAN Dissect. They were looking for a way to interpret which neurons were actually responsible for activating some stuff. So in this case, we have, let's just see, okay. We have this church, which is generated by the network. We want to activate the neurons for the tree, and we want to force them to be active in this area. And guess what you obtain? Well, trees here. Let's just make it again. If I select the grass neurons and I draw here instead, what you obtain is a nice grass here. And in case we select the cloud neurons and then we force to deactivate them, what we obtain is a less cloudy sky, because we deactivated neurons that were responsible for generating the clouds. So this is a very nice way to actually understand how this thing works. Moreover, we are able to do image-to-image translation. So one of these is real and the other is fake. Which one is the real, left or right? Left, exactly. This is perfectly generated by computer. So from a winter setting, it went from a spring setting. Which is the real one? Left or right? Right. Right is the fake. I can also change the setting from day to night. Actually, they found out that when we transpose from a domain which has less details to a richer detail, it's much more difficult, because you have to generate more stuff, actually. Instead, here, you are cutting away, so the image looks more realistic. How does it work? So, since everything is unsupervised, we take a bunch of images in the night setting, a bunch of images in the winter setting, a bunch of images in the spring setting, and so on. We put it in different sets. And then we have to learn a mapping function that learns a concept which is in between the two sets. And then we learn functions that lets us jump from one set to another. So images in different domains can be mapped to a same latent representation over a shared latent space. So what we do, we use a variational autoencoder to train a latent space. And then we condition coupled GANs. Coupled GANs are a way in which we take two GANs and we bind together the higher level weights. So in this case, this GAN and this GAN are using the actually same weight to perform these the first steps. Why? Because if I want to generate a tree, if I couple the two different guns, a gun which is on the winter and a gun which is on the spring, if I force it to use the same weight in the lowest level are those that generate the main picture, and then the highest levels are responsible for the details, I will be forced to generate the very same image, at least the contours, and then the details will be very much conditioned on the domains this GAN is mapped to. So if I take a winter and spring images and train a shared space, and then I feed it toward GANs that generate in different settings, and I do the same with the vise, for example. So I bind the highest level in this case, which are the ones that capture the hierarchically most important settings, while the details are in the first levels here. I will be forced to learn a shared representation. That's the trick, actually. In this case, we force the similarity in higher order features by this trick. And then we have the different discriminators that do the finishing touch, where we have to understand if it's a good image or not. We can generate also audio, but with even more complicated architecture. This is tachotron. This is a convolutional toward the recurrent network with an attention model in between. What does it mean? This is a text-to-speech in which you put characters. You just extrapolate the characters embedding with the different modules, and then you generate one audio sample in spectrogram frequency at a time. Then you fuse all these spectrogram representation, and then you get a linear waveform representation that gives you audio. And as usual, I have a sample of this. This is actually the audio generated by the network.
Generative adversarial network or variational autoencoder.
Or
Basilar membrane and otolaryngology are not autocorrelations.
completely bullshit utterances. But the idea is that this technology, tachotron, is the one that powers your Android phone, actually. So whenever you have your text-to-speech that you use in Google Map, it's this technology, actually, that has been implemented. So today we have seen the three main models of generative AI, and we have actually seen some demos. Here I leave you some references, which are the main points that you want to maybe study. Some of these are videos, some of these are actually articles. And well, that's it. Thank you all.